So remember the equation is negative EMF over di dt, and then the EMF is negative NA dB dt, and then the negatives cancel, and then the B is equal to the B of a coil and mu 0 I over 2R. I'm using the B at the center of the coil, right? So I'm going to assume the coil is small, so it's that the center is a average sort of value for the B field. So then you're going to have divided by di dt. Then you're going to have what L is NA, and then the N mu 0 over 2R is going to come out, and di dt is going to cancel the di dt again. So it's just N mu 0 over 2R, and then you're going to have A is going to equal pi R squared. So N squared pi R squared mu 0 over 2R. Okay, and then the R cancels the R, right? And then you have N0 pi R mu 0 over 2. Then, of course, if you put a metal material in there, so we could just change this to just mu, depending on whatever the relative permeability of that material is. Okay, so then that would be the inductance of a coil. Then a toroid. So then what will the toroid be? There was a lot of these, right, in those pictures. So then L is negative N A, then dB dt over di dt. So the negatives cancel, and then A. So A is this area, the surface area of the toroid, the cross section of the toroid right there. Right? Yeah. Negative NA, and then dB dt, the B would be the B field inside of a toroid, which is N mu 0 I over 2 pi R over di dt. Right? So in order to get a value without having to integrate this, because technically we should be integrating because the R here is different than the R here. You see, you're further out from the center. So we should be integrating this, but if I want to kind of not integrate, what I can do is use R as the average R from here to the middle, right? And that'll be the average from the center of the toroid to the middle, all the way from here to the middle of the toroid, and that'll be the average value of the R. So then the di dt will cancel, and I'll have N squared A mu 0 over 2 pi R average. Right? And now, what will A be? What we could do is we can have an inner radius R1, and then outer radius R2. So R1 plus R2 over 2 is our average. You see, so we can kind of come up with an equation with inner radius and outer radius. So inner being from here to the inside of the toroid to here to the outside of the toroid. Inner plus outer over 2, that gives you our average. And then the area is going to be what? The area of, so imagine like this, that area. So how do we calculate that area? It's like a donut, you see. It's going like this, then coming back around. So if this is R1 and this guy is R2, so our average is going to be this plus this divided by 2. So that's that. And then the area is going to be this guy. So to get the area, I can do R2 minus R1. That'll give me the diameter. And then divide that by 2, right? That'll give me the radius of this guy. And then I can do pi r squared. So R2 minus R1 over 2, right, is going to be the diameter, the radius of this guy. R2 minus R1 over 2. So then I could do the area is pi times this guy squared. So let's see what we get here. So inductance is equal to n squared mu. So then mu 0 I can replace again with mu in case there's a metal material in there. So n squared mu over 2 pi. And then our average is going to be R1 plus R2 over 2. And then area is going to be pi times this guy squared, right? Okay, so then what's that going to be? Pi cancels. 2 and the 2 cancels. So L is equal to n squared mu. So then you have here R2 minus R1 squared over R1 plus R2 over, and then 2 squared, so that's going to be 4. Right? L squared mu 4 R2 minus R1 squared, R1 plus R2. Cool. So that's the inductance of a general toroid. Now, if the inner radius is 0, because you could have a toroid that's like this. It's wrapped like this. So in other words, there is no gap in the center, you know, and then you could put a metal material all around without needing necessarily a gap. In the pictures, a lot of them did have gaps, but you don't necessarily need them. You see here? You see how there's a gap here in the middle? But if you don't want the gap, you could just have a closed circle there. So then what would be the equation for a closed, no gap toroid? So then the R1 will be 0, right? R1 will be 0, then it'll be easier. This disappears, then you just have R2 squared over R2, and you just have R2 on the top. So then it just becomes n squared mu R2 squared over R2. So just R2 over, and then this is 0, so just over 4. That's it. I think that's it. Let's see, n squared a mu 0 2 pi r. They're all equal to some n squared. They're all proportional to the number of turns squared. So if you want a bigger inductor, just have more loops of wire, you know, wind it up more.